And this is inside Rhinoceros modeling system, so it's a sort of well-used package. So here I'm going to attempt to make that same blend inside this particular shape. So I have to choose both surfaces. I have to go through and select the two surfaces that I want for every single intersection, which takes a lot of time if you're doing something complicated. And then I get this behavior. It's absolutely crazy. And this actually happens. You think, well, how is anybody using it? We hear about 3D all the time. How's this stuff being used? How's it possible? Well, it is. This is actually what happens, and designers will go in and literally trim these edges and fit them together, try to make them fit, which means there's actually a crack there again, and you don't have a closed object, which for manufacturing is very difficult. How does the machine know what's inside and what's outside? You don't know. Started it. So the sort of solution that we've come up with is there's a couple different components to it, but internally at our company we call it Digital Materialization. It also happens to be the title of my PhD. And of course Digital Materialization Group that I was talking about earlier is named after this. It comes from 25 years of research. It fundamentally says that we have to represent things symbolically, and we have to do it with mathematics. So we've been working with something called function representation, which is very different than the kinds of boundaries that I was showing you earlier. It represents things not as 2D surfaces, but as a three-dimensional mathematical object. And we do that with a language that we've developed initially before our company. It was called Hyperfun. So you can go to hyperfun.org and you can look at that language. And it's kind of a programming language for shapes. So this shape right here is literally represented by the code you're seeing on the screen. And this used to be how we would model back in like 1998, 1999. This was our modeling system. So it wasn't graphical, it was very difficult. But it was the only way to do it. Computers weren't fast enough at that time. Because what we do takes a lot of computation, doesn't take a lot of memory. This structure is kind of, I like to also note or point out, this is honeycomb made by human, this is honeycomb made by bee. It's really fundamentally different. If you look here, there's these sort of blends between these containers. And that's because this is done by a very different style. Bees actually spin around when they produce this. So this is actually a kind of spherical packing. So we've got two different unit cells. They're slightly different in shape. If you look here, you can see that what we've done is we've taken this regular grid, and here we have one type, and here it becomes another. And in between, you can see there's some shape that seamlessly morphs from one to the other. So again, when I was showing you the interpolation between functions, in this case, we're just interpolating over space between these two different shapes. We're not actually moving vector points or anything like that. So you can create really complicated relationships very quickly. And of course, distorting space again, like I was showing earlier. And just to prove that again, here's another example where we're taking a sphere and we're morphing it into this object here. So very dynamic kinds of cellular structures can be made. This is inside a half ball. We sort of use this as a test often. And in this one, we're taking that object you saw earlier and we're actually shrinking it to the outer edge of the shell. So we can have deformation of the object over space or in relation to another object as feedback. And we can actually do surface kinds of manipulations as well, where we search for the surface and then we base microstructures across the surface. And we can make microstructures from microstructures. So if you see here, this is a microstructure. We zoom in, we see that there's something else going on here, and indeed there's another microstructure. I've done the ball I showed earlier, but it looks kind of crazy, so I can't show a slide of it because it's nonsensical. But this is done on a GPU right now. Our current system that we are going to make available, hopefully on the market in the next month or so, isn't using a GPU. It uses the CPU only. But we do have a GPU version in the works, and you can see how dense this is. And for us, there's almost no slowdown in the frame rate because it's not based on meshes. It's per pixel rendering. But it's solving for the function in the entire space. And here again, you see it. And this is much more fun, of course, because we've got all these lovely blends in here. And so that's being dynamically. This is not an animation. This was a screen capture of someone dynamically moving this around and manipulating it. So just to sort of emphasize that, here again is the unit cell you saw earlier. STL mesh fails really rapidly for this object right here. I was just working on this here at CTI over the last week. It's 150 megs at 200 microns, which isn't anywhere near close what we want. Versus about 4K for infinite resolution for this object over here. And actually, if I extended that object and made it much, much larger, it would remain 4K. So, whereas this would exponentially increase, this one here, or at least double. Yeah. I still wouldn't run the numbers on it. So here's the sphere you saw earlier. It's one of the objects we've been working with direct printing, and to some success. We still have a lot further to go. None of these printers, unfortunately, all the commercial printers are locked into the STL world because that's how CAD works today. So they didn't think that anybody else wanted to do anything else. So they've sort of stayed in this world where you provide them with an STL, a mesh file, and they create the slices. What we want to do is output the slices directly to the machine. So we want to slice it ourselves at the resolution of the machine. So the motto with us is that everything should be at the resolution of the machine. So if you're rendering something, it's at the resolution of your screen. If you're outputting to a printer, it's at the resolution of the printer. And here's some other objects we've done sort of with direct printing. Plastics, UV plastics. This is silver, actually. That was done. Yeah, well, the silver process was actually sort of part of it was implemented on your machine, Evan. And thankfully, because I can talk to Evan's machine directly because it's open. And this is done on a Roland milling machine. So that's a subtractive process, the first one. Little teeny ant. Wax. Yeah, let me show you this. I'll have to come back. So this is an example of the slices that we do. So this is just one example of the kind of slicing we do. This is with a gradient material, so the red would be one material, the green would be another. And this is going through the object you saw earlier, slice by slice. This is currently in the hands of Objet. They've told me that I can't access their printer, but if I sent them images, they would maybe do it for me. I haven't heard back from them yet. We'll see. So, but more interesting, the gradient material is kind of nice just to show that we can actually grade from one material to another. It doesn't have to be this explicit, like there's one material and then another material. But we can actually define gradients as you see in nature. The other, do I have it? Yes. So this is another example with complex distribution. These are discrete distribution. I could have blended this as well, but we haven't done it. We're trying to see if they can print this. So this is one material inside for the structure, and where the blends are on the outside, we have another material in the green. So we're hoping to get that printed as well. So you can see you can make some print. And this is, so what this is layer by layer of that object, slice by slice, as it would be printed. Okay? So that's sort of the state of the art in terms of our output. For direct input, what we've been working on is the notion that, again, we don't want to work with STL. We've got sort of an issue with being backwards compatible in some sense because we do things so differently. So we've been working on bringing in things in a really direct way. Of course, CTI has been doing this great stuff with Infosarius. We're fans of this piece of software, and this software is great for visualization. Currently, as I understand the process here, when they want to do more than that, they export an STL file from this, they take it into Rhino, and inside Rhinoceros, they build NURB surfaces using the mesh as a reference. There's a lot of sort of issues with that. One is the amount of time. And the other one is that there's some accuracy issues, although I think the guys here try to do the best they can to make sure that there's some fair balance between the amount of time it takes them and the accuracy that they get. But what might be better than that is that we go directly, that we're able to actually grab even meshes, potentially in the future, but at least for right now, that we're able to grab STL files and bring them into the system and allow you to start modeling with them immediately. Okay? And that you don't have to deal with these surfaces, that you can just interact with the object like any other function in our system. And we've actually done that. Let me see if this works. Again, I'm going to give you a little demo here. I think it's been screwed in. So what you were just seeing there was a voxel set that we've brought into our system. That's of a, am I correct, is that a rabbit's heart, or what is that? Rabbit skin. In the skin. Okay, so very fine. That's why we have some noise. Let me get out my mouse. Oh, nope, it's over here. Wrong one. I thought I had it plugged in, but I didn't. Okay. So, okay. So as you saw, that was a skull. We can rotate this around. And so this is a voxel set that we've brought into our system, into Rhinoceros, and that is now seen as any other primitive in our system. So I could put microstructure in that. I could subtract objects from it. I could add objects. I can bend it. I can morph it. I could combine it with another voxel set. So I could chop off the head and stick someone, chop off the top of the head and stick someone else's, the top of their skull on this model if I wanted to. And you can see that we've done a pretty good job of making it fast, fairly quick. Let's see if, I don't know if this will work today. This is all beta software and experimental, so you'll have to bear with me. So you're seeing inside the skull now. So we're actually inside the head. Should be. Oh, let's zoom out just a bit. Oh no, I didn't get through, did I? Let's rotate it around. Yeah, there we are. So you're now inside the actual head, and you could go in here. You can imagine that if you wanted to. So one of the applications, of course, would be if you saw this individual unfortunately had a very serious injury, as I understood, from a motorcycle. So what we could do is we could actually work on making a patch for that in our system in a way that in the future would be much easier than what is currently being done to model that stuff. And in terms of putting screws in or checking for operations that you might want to do, or even medical guides, right? This could be done very quickly if you've got the ability to input this data. In addition, I'll show you another example of actually modification here. So here we have the vascular system I showed you earlier. Okay, so this is the vascular system I showed you just a second ago of the skin. You can imagine that somebody would want to, there we go. So what we have here, this has been drawn by me as a CAD object. So you can imagine that if you had this vascular system and you had some destroyed organ in the body, that you would want to, where the destroyed organ was, obviously you don't want to take that data. And maybe they didn't take a scan earlier. I mean, ideally everybody's going to scan their bodies, right, and have a perfectly healthy body that's been scanned. But you might not have that information, so what you need to do is go in and model the healthy organ, or at least parts of it. In this case, this can be done very quickly. I simply modeled this and simply said union between these two objects. Anybody who's familiar with CAD would understand that that's something you just normally can't do. And again, we're using the voxel set directly, so that's actually the exact data. Now, there has been some discussion about, do we want to smooth that data out? And we can do that too. We haven't done it yet, but then we lose some accuracy. We're actually sort of starting a project to do BioCAD with CTI. That's our up-and-coming plan. Operating in that environment, taking a look at the different objects, selecting some subset of the voxels and instantly converting them into a CAD object that you could use, for instance, to put microstructure in, to define cell types, to extend in some way. For the geeks. But thank you very much. That's it.